And it is useful to keep in mind that there is no magic here, but the sufficient number of small things connected together can look like magic. Okay, there was a raised hand. Yes.
What happens if we skip more than one?
What?
Like in that network, you were skipping one node, and what happens if I skip more than one?
You can try. You can call whatever. What's your name?
Prabhat.
Prabhat network. There you go. Right? You can try that. I mean, in general, again, that's the reality. If there is a nice way in which you can mathematically prove that some idea is better than other idea, then there will be much fewer people who have a chance to be machine learning people. Right now, everybody, in fact, all you guys, I can guarantee you, if you want, I'll come and sign a certificate. You're like the 99 percentile of machine learning people, because the entire universe thinks they are machine learning people. Okay. Okay. So as I said, this one is actually basically, you notice that this is the real image, because you can actually see the image, and the next layer is actually understandable to you. Okay, but when you start doing convolutions on this, and in fact you do directly do convolution on this image, you first do max pooling, then you do ReLU, and then do again a convolution. By that time, the connection to the real image and what you are seeing is completely gone. Okay? So now we'll finally get to the convolutional network architectures. I'm assuming that you read the very nicely written Karpathy write-up on this, including beautiful animation, right? So I'm just going to walk you through this once again. If you have any questions, this is your time to ask. So essentially, as I said, there is going to be a conv layer, there's a ReLU layer, and there's a pool layer, and it's repeated. Start, linear plus number of times. Okay, and then in the end, you put an FC layer, fully connected layer. Now, you have to understand that you could actually put fully connected layer everywhere, and you don't lose expressiveness. That means any network which has only fully connected layers everywhere will do as well as a convolutional network, modulo you have enough data to train it, and that there is no overflow. But on the other hand, without a fully connected layer, if you just put the convolutions everywhere, actually that basically loses expressiveness. Because convolutional layers are assuming certain kinds of locality in the image. Okay? Fine. So then, and then basically, as we pointed out, so ConvNet will compute the, I'm not sure, are there any questions on this? So you have convolution, you have the ReLU. ReLU can be any other threshold. Any other threshold. So in this particular case, one of the things that you will see is you started with input. This is useful. We'll spend a little bit more time on how the input size is treated. We started the input with a 32 pixels by 32 pixels by 3 layers. Right? Because the layer corresponding to R, one corresponding to G, one corresponding to B. So it is useful to think, if it helps you, it's useful to think of inputs and the intermediate outputs of the network as volumes. The image itself is a volume, it's 32 by 32 by 3. Right? Now what is going to happen is, imagine I only had actually one filter in my convolutional kernel. Then that filter would be applied to the R layer, and it would get, when it applies to the R layer, it will get something like this. It will apply to the G layer, it will get something again like this. B layer, it will get another thing like this. And so you stack them up. So now you have an image which is 3 deep here, and a volume again which is 3 deep here. Now imagine, instead of having just one filter, I have a bank of filters. I call kernels as filters also. Okay, because filters is the name, if you remember, people used to call these Gabor filters. These are all named filters. Okay. So if you actually put, let's say, decided to put a bank of, let's say, 2 filters, So then for this R layer, you apply both the filters, you get 2 squares. So you have 2 depth. For the G layer, you get another 2 depth. The B layer, you get another 2 depth. All of a sudden, after the 2 banks, you now have a volume which is 6. Do people see this? Okay? But it's the same idea. It's just that now all these filters can be different weights. In fact, they will be different weights. Each single filter has only one set of weights. And who gets those weights? The guy in the very last row. The guy in the olive green shirt. The guy who might not actually be here. What did I tell last time? What did I tell last time? If you were here in the class last time, I said if you want to spend time looking at your laptop, come to the front or leave the class. Okay? It's not going to be repeated again, please. So do you have an answer to my question or were you sleeping? Okay, so do you have an answer to my question? What? So we were. I forgot my question. Yeah, who gets the weights? Yeah, this is what I try not to do this because it actually kills the flow of the class. In fact, what you are doing by not paying the class is distracting me enough that you are making the rest of the people suffer by it. That's why please don't do it. If you want to insult me, that's completely fine. But it also affects my flow because I keep looking at the fact that people are not paying attention, I do things. Anyway, so who is getting the weights? How do you get the weights in each of these filters? Somebody speak up. It doesn't have to be the olive guy, somebody else.
They are already given for installation.
Okay, so this guy says those weights will be given. How many people agree with him? How many people have a different answer?
Through back propagation.
This guy seems to think it will be done by back propagation. How many people agree with him? At least more fancy name. So the rest of you, any other answer? Yes?
Could be either reaching filters or they can be
Mostly what is the case? But a 150 layer network, what is the case? What did the Microsoft guys do for this 150 layer network? Did they buy a large number of cheap paid labor and make them make filters? Or what? They learned the filters.
Yeah.
If this wasn't obvious to you, and I was thinking I will put the olive guy on spot, but apparently I put the entire class on spot. Okay, so it's like those weights are going to be learned. In the beginning, you initialize them to semi-arbitrary numbers. Through backpropagation, those weights will slowly change. By the time you're using the network, those weights are already essentially converged to some random numbers. And then that's what I'm showing you here. It's very important that you understand. I thought I said this, but what I think I say versus what you get are completely different. Yes?
So in the past, they used to be custom made by people, but now they
Yes, so if you make them, then you will make about 5 or 6 different kinds of filters, and that's the end of that. This 150 layer network will probably have maybe 10,000 or so filters, in essence, are being learned. If you assume a filter is the entire thing, and actually the filters have lots of weights. So each weight is actually a parameter to some filter. The strangest thing that you need to wrap your head around about neural networks is sort of like coral reefs. That's how my mind works. You know how coral reefs work? Have you been to coral reefs? Right? Have you been to Barrier Reefs? I mean, of course, if you haven't, by next year they'll all be gone. There's this thing called global warming, and it's all taken care of. So maybe before semester ends go. But coral reefs are these amazingly beautiful things, right? But how are they formed? It's these little things kind of secreting. It's their poo, essentially. That's what coral reefs are. And this is why, if they are not there, if you you want to grow one, it will take millions of years. Which is why people are telling, please let's deal with some global warming situation. So individual corals are essentially done like a little microgram by microgram by microgram, and you have barrier reef. That's what neural networks are doing. This basically, in a 150 layer network, each weight is being changed a little by little by little by little using the back propagation. In the past, it also used to take million years to do this, which is why we thought neural networks are not working. Now we can basically speed up because we have GPUs. And so essentially you get to the change values faster. This is a very useful analogy to have in mind to lose some of the magic of where those numbers are coming from. Okay? And not only this is like mind-boggling, because you also remember we talked about SGD versus batch gradient descent. Gradient signal itself is a pretty weak signal. When you do stochastic gradient descent, it's also noisy. It's crazy that the damn thing works. You see what I'm saying? It's also crazy that there are coral reefs. Okay? That's a way to think about it. Yes, yes.
If you're going to be learning the weights within 150 layers, is it important for the initial input weights or the initial weights to all be instantiated in the same place, or can they just be?
No, that was why in the last class we talked about the slide of initializing weights using either Xavier initialization or actually learn to renormalize weights, renormalize inputs using batch norm. Again, all those pieces are being talked about. The issue is all of them have to come coalesce together. Otherwise, you would understand neural networks at the popular West level. That there's a big network, some magic happens, and then cats will be seen everywhere. Okay, that's, you need to take my class and go through my torture to get that. You can read, I guess, any tabloid, yes.
The size of the dimensions of the filter itself, is it learned or is that something 3 by 8?
Those are hyperparameters. That's what we're talking about. Hyperparameter means you need to skill set them. Okay.
So there's 150 layers, but does it matter how many nodes are in each layer? Like, is it like 150 of like a single node?
No, but the number of nodes in some sense is connected to the size of the kernel. That's what it is really. Because that's the other thing that you have to wrap your mind around. The fully connected network is extremely easy to understand. It has the exact same, topology everywhere. Here, in essence, you have, as I mentioned when I showed you the fully connected thing, the best way to understand convolutional networks is instead of putting a layer which is this wide, you actually decided to just have these many units. But they will essentially move on the input up and down. Okay? And so of course, and whenever they are being connected to the input nodes, they will be connected by the same exact weights. And so the number of weights is much fewer compared to the fully connected network. And so the size of the number of nodes will be how big is your kernel. In the single dimensions, this is my kernel size. If I think of it as the image, then my kernel would be like a square, for example.
Does the convolution network have dropout, or is it just purely?
They also do dropout. Everything we talked about happens everywhere.
Okay. Just making sure.
Right?
So
that's how the magic happens.
So the dropout would be when the weight is good down to 0?
So some weights you basically decide not to update in a particular epoch.
Okay. So just because like this one node just became pointless because it's not adding.
Yeah, in that particular time, in the dropout at a particular epoch, you don't wind up. That's why, I discuss dropout using the fully connected networks, and then I say the same way it works for more complex ones. You could argue, honestly, that the convolutional networks are less general than the fully connected networks, or more general. They're syntactically more general because syntactically they have more syntactic funny things like the same kernel moving up and down. Semantically they're actually less general because everything convolutional networks can do, fully connected networks can do, not vice versa. If all of this, if you understand this, that's where you're getting close to understanding what's going on. Yes?
Yeah, so like the ResNet is like 150 layers. So can we replace it with like all fully connected layers with less number of layers?
You could try. So all we can do right now is something hasn't basically yet been done. It's either because people didn't have chance to work on it, or somebody worked on it and didn't actually say. So in fact, one of the crazy things that happens in science is many ideas that don't work, when people try them and they don't work, they don't bother, they don't get any work for it. Honestly, civilization would be much happier if you also get to write a paper saying, you would have thought this idea will work. I spent about 25 years of my life. It doesn't work. You see what I'm saying? Instead, basically, I too will spend, right after you give up, I spend the same amount of time again. Unfortunately, lots of people might have read lots of ideas that don't work, and people don't write papers on that. The only good thing right now is there are blogs in addition to papers. And so you can read these blogs and see what they say. But they're very noisy. They may have dreamed that they have done it. They may not have actually done it. Yes, there was another question somewhere in the back. Yes?
Can you explain what you mean when you say that the kernels are moving up and down? Like, are you referring to the strides? Like an entire
Yes.
kernel?
Yes.
Okay.
We just couldn't go that in a minute. Okay. So again, so in fact, in this particular case, if I only have these 5, then I can, let's say, start from here. In this case, it would be connected. This would be connected to this. This would be connected to this, etc. And then the question is, again, I want to move it. How much do I move? If I move by 1 unit, basically that's like the stride. In the case of images, the whole thing is in terms of squares. In the case of this is, in fact, images can be written this way. It would just be raster scan version of the image. Yes?
Regarding the amount of data that we need to properly train a ConvNet, is there any way of knowing without actually trying to train?
No. No. So you keep that in mind. I'll show you a joke in a minute. It just, you know that there are way fewer parameters in a ConvNet than the comparably sized fully connected network. Right? So let me show you the joke. And you need to understand some jokes. To understand a joke, you need to understand the background. Okay, so last week or so, there was a big New York Times article saying that all of you guys are going to be paid humongous amounts of money. Right? Very soon. Because AI is extremely hot. Okay? And then it's amazing what salaries they're getting. And then so Jan LeCun, he has this parody account, and then so he basically said this, that salaries in AI are growing fast, but salaries per parameter are growing faster thanks to more convolutional networks. To understand this, again, how many of you know Reduced Shakespeare Company? Yes, only one person. I don't know where is the culture going anyway. But so Reduced Shakespeare Company is this very funny parody of Shakespeare. And then their tagline is, the more you understand the original, the more you will find us funny. The more you understand convolutional networks, the more of these jokes you will understand. Okay? So anyway, this one, because per parameter, you have much fewer parameters to get to the same level of accuracy. So you could say that. Anyway. Okay. So we were here, and then we understood, I hope, that it is useful to think of these things in terms of volumes. The image itself is a volume, and after the first convolutional plus max pool plus the ReLU layer, okay, it becomes still a volume. It's a volume possibly of the smaller face size, probably bigger depth, because the depth depends on the number of filters that you're using. Okay? One of the other things to understand actually is previously the FC layers, all layers are of one type. Here now conv layers are one type, they actually have weights that you have to learn. Maxful layer is another type where all it does is it takes the maximum in one particular region and just takes that number. Okay, and so there are no weights to be learned in a maxful layer. Similarly, for ReLU layer, there is no weights to be learned because it just basically takes max of 0 or x. Okay, so some of the layers are actually parameterless, some layers are parameters, the ones with the convolution. Okay, so, and then, so this is how, if you try to visualize these, first of all you have to understand that actually you can't visualize this. This is some crazy volume. You don't know how to visualize a volume. But if you try to essentially do some visualization, there is one particular idea called TSV that people use to kind of feel good about maybe I understand what's going on in the network. Then essentially this is how it might look if you visualize. So you may have a car picture here and the original convolutions are looking like this, then you do ReLU, then you do convolutions again, then you do ReLU, convolutions. By the time you come here, you don't see any patterns here. The earlier on, they somehow you might still see like outlines of a car. And then in the end, you have a fully connected layer, which then gives out essentially, spits out a probability of the top 5 classes. Okay, now how do you get the final one? Basically, by the way, you don't use ReLU for the final layer, you use typically sigmoid, a logistic threshold. Okay, that's how you wind up getting that. Now, people mentioned strides and you already thought about it, that things are moving bit by bit by bit. So here is a bunch of syntax. So you have essentially the image itself has a volume and it's like a 3 volume, and in essence what you're doing is you are working and there are a bank of filters, and these bank of filters are working on these volumes and they get a bank of values. Okay, in the volume that you take a small region, and that region you apply the filter, you get one number. So this particular region in the image leads to this particular 2. And that's how this whole thing becomes this thing. That's the conceptual way of understanding what's going on. So then there is this question of kernel or filter size, which is how big is the, I'm assuming you all read this, I'm just walking you through it again. How big is the convolutional kernel, which is, you can think of it as the mask. And in general, one of the interesting things is in the beginning, people used to use big kernels. In fact, AlexNet used a 11 by 11 kernel. Right now, the conventional wisdom, to the extent there can be conventional wisdom for something that was sort of starting around 2012, is that smaller kernel sizes are better. Okay? So typically people use 3 by 3 or even smaller kernel sizes, filter sizes. But AlexNet actually uses 11 by 11. Again, this whole thing sounds very engineering-ish. You know, why would you do it? Because it seems to work, essentially. Okay? Stride, which is how is the kernel slid on the image. So you put the kernel on, let's say, on this part of the image. Then when you move, how much do you move? The minimum is you have to move by 1 pixel. That would be 1 stride. If 0 stride means you just sit where you are, you're not moving. 1 stride means you're moving 1 by 1 by 1. And when you move by 1, in essence, if you are, let's say, a 3 by 3 filter, previously you took a 3 by 3 region in the image, then you moved 1, then 2 of the columns that you saw previously are still going to be present in the next time you're seeing. So you're essentially having the same part of the, some parts of the image take part in multiple filter scans. So that's, the bigger the stride, the less of that happens. So if a 3 by 3 kernel, if you do a stride of 3, then every time you go to a different place, you are essentially looking at a completely different set of image numbers. The smaller stride means you have overlap. Then there is this issue of padding. The padding issue is that you have an image. Now the problem is that if you are talking about the kernel being moved on this image, depending on the size of the kernel and size of the image, in fact the output might be smaller than the original image. In fact, they may not even be integral. Okay? So the question then is put padding, these are all zeros. and act as if this bigger thing is the image, and then start actually going from here. If you do that, you are essentially taking padding into account. Okay, and by doing the padding, actually, you can actually, the most useful thing, because the reason you do padding is so that the input and output sizes are the same, if you want them to be. Okay, but you can actually make the output size even bigger, but then most of that would be again a padded image, because assuming that all your padding is zeros, you can pad zeros, many rows and columns around the image. Okay. So without the padding, the output of the kernel filter will be smaller than the original image. And then the other final question is the number of filters. How many filters are you going to use? Okay, and that essentially again increases the depth. So if you have one filter, there will be a 3 depth in this level. If you have 5 filters, there will be 15 depth. Yes? Yes?
Okay, so I know that you do the zero padding so that the output size is the same as the input size, but why do we need for that to happen? Like, why is it that we can only decrease the size in pooling?
Again, so for many of the, I'm sorry, what's the second part of your question? Why do you need to do
I mean,
this?
I know like the point is so that like you're only decreasing the size of the structure like when you do the mass pooling, but why is it that we can't decrease the size in the context?
You could do. It is just that it actually tells it's a better story this way, honestly. Okay, I don't think there is any work that has been done to show that padding helps versus hurts. It's a much better story this way because there's only one guy who's reducing the size, that is the pooling guy, and the other guys are keeping the size the same. Okay, that's my best answer, because I don't know of any literature which actually showed that padding actually helps, other than for the syntactic issue. Okay? Okay, so then finally, like one formula, right? I mean, you need to have formula. There's like this entire neural networks is completely devoid of formulas because everything is happening in a gradient, and other than that, it's just adding and multiplication. So this is like this is why, as I said, some of the neural networks the books right now are written with no mathematical expressions, which also helps the universe becoming a machine learning powerhouse. Okay, so if you think of a W by W image with an F by F kernel and a stride S and P0 padding, that means P rows and columns around the image are padded, then output size will be O by O, where O is this W minus F plus 2P by S plus 1. So as an example, if you have a 7 by 7 input image, the 3 by 3 filter, so this is W, this is F, stride S is 1, pad 0 is P. So you can plug in those numbers and you will get that basically 5 by 5. And you should be able to convince yourself. This is just simple geometry. Now what about the depth of this? So this will be a 5 by 5 rectanguloid. How deep is it going to be? It's going to be as deep as number of filters times 3, where 3 is the original input, is RG. Okay? So in the case of AlexNet example that I showed you earlier, the image size is actually a little bigger, 227 by 227. The kernel size is 11, the first time around when we did it in 2012. The stride he used was 3, he was making a bigger jump. Okay, padding was 0, and so the output size would be 55. And the number of filters was 96. And I'm assuming that basically they were using grayscale images, in which case the depth will still be just 96. If not, it will be 96 times 3. Okay, so that's what is happening in essence. Okay, and then in fact, as you read, that essentially there are all sorts of funny things. Apparently, that particular paper was so influential in the last few years that small things that that guy did writing that paper, including to fit it in the paper, he cut out the architecture diagram a little bit more. So because of which some edges in the architecture diagram were missing, and so people tried to make sense of what was the actual architecture, essentially. So it's that level of influence it had. And in particular, apparently, the original paper says that the image size is actually 224 by 224, and if it is the case, then in fact these numbers won't make sense, neither does the rest of their paper. You must have used 224 with 3 padding. That's it. Yes?
Is it fair to be able to draw a connection between these sizes and directly the number of nodes in the layer? Is the number of nodes in the first layer 227 times 227, and the second layer 11 times 11?
No. The number of nodes, the node again, a node is the kernel. So if you have f by f kernel, okay, you have f square weights. Okay? And so if you have one filter which is f by f, you have f square weights you need to learn. If you have 10 filters, then you need 10 times f square weights. Please understand that the nodes are the elements of the filter. That's what you're trying to learn. I mean, it's hard to, it's much easier to think of the fully connected network because it's all, looks like it's nodes. Here the nodes are moving. Again, go back to this. Anytime you are in question, think of this as this is my kernel. If this is my kernel, all I need to know is actually the weights connected to this. In our particular, in ConvNet, essentially the kernel size, the weights are essentially the elements of the filter itself. So in fact here the analogy falls flat a bit here because essentially you are considering only the weights connected to these nodes, and the weights correspond to the elements in the filter. So coming back to your question, if you have an f by f filter, then it needs f square weights that you need to learn. Okay? And if you have k of them, you need k times f square weights. And these are the ones you are essentially initializing. Yes?
Does this only work on the same size image that it's trained on?
Right now, yes. But then you can pattern it. Okay? More or less that's true, actually. Yes?
Are we decreasing the image size of the input because the layers that we are putting are 200 into 200? Images are bigger than
No, this is for AlexNet. Right now they have bigger images.
So we can put...
Yeah. They can take much bigger, 700 by 700 for example. It depends on how big your image is. Okay? And if you want high res, then you have bigger and bigger sizes, essentially. Okay? Okay. So, any questions on how this? Yes, please.
So every convolution layer will have the same filters?
Every convolution layer, let's say a particular convolution layer, let's say, has 10 filters. Each of those filters